Okay, we have this heat equation where we have that the initial condition, some function fx, and for the boundary condition, it says that both ends are insulated. That means that if we have the rod here is 0 and here x equal to L, that means there are insulated here and here. That means there are not heat. The heat crossing here it's 0. So the amount of heat crossing here is also 0. So when x equal to 0, you have that amount of heat is 0. That means you have the area minus the area K, which is conductivity, and you have temperature gradient 0. These two are constant. That means when x equal to 0. The same when x equal to L, you have no heat crossing. This leads you to the x equal to 0. Then you have both boundary conditions. The x when x equal to 0 equal to 0, and you have delta u delta x when x equal to L equal to 0. Like that. Okay, now we have this condition. Now I have to solve the problem. I'm gonna use separation of variables, but from my previous video I actually did all of that. The first step, you should watch that. So here I will just go quick, but I'll just solve it quickly. Okay, I'll just stop for sign. I won't actually go for the case when I get a hyperbolic sine and cos, because usually they don't lead to the solution. So I'll just stop for case 1 and case 2. Now I need to find a constant C2, C3, C4, and C5. Sorry. Yeah, okay, for the boundary condition, I'm gonna use the boundary conditions for this part here to find these constants. And we have that u equal to x times t. That means du dx equal to x t. And then when I set to 0, that leads to x equal to 0. This is the condition. When x equal to 0, I get, and when x equal to L, these are my conditions. This condition came from transforming the boundary conditions, these boundary conditions, to find this constant. So we transformed, we use the separation variable actually to find this constant. So these are the conditions I'm gonna use. Okay, now to find C2 and C3, I need to find first derivative. It's just C2. Then if I sub the condition, leads to C2 equal to 0. Then that means I have x equal to C3 because C2 equal to 0, right? There is no way from this condition to find C3. So I'm going to leave it just like that. That means ux t, which is equal to x times t, is going to be C3 times t, where t equal to C1 e k lambda t. But remember that lambda equal to 0 for this case. So that leads to C1 times C3. Then I'm going to say, okay, this is just some big C1. I'm going to say some big C1. Okay, I'm going to say some C0 because it depends on lambda 0. Okay, now that means uxt is just some C0. Now I come here to this condition. Okay, I have also the condition 0 equal to 0, and I have L equal to 0. That means the first derivative gives me minus C4 alpha sine alpha x plus C5 alpha cos alpha x. 0, I get C5 alpha equal to 0. That means C5 is just 0. Then I have L from here minus C4 alpha sine alpha L plus C5 is 0. All of this has to be equal to 0. C4 alpha sine alpha L equal to 0. Also the same, if I set C4 to 0, then everything is 0, there's no solution. I'm going to say C4 different than 0 imply that sine of alpha L has to be equal to 0. Alpha L has to be equal to n pi. For n equal to 1, 2, 3, and so on. That means alpha equal to n pi over L. Then the solution x equal to C4 cos n pi, which is alpha times x, n equal to 1, n equal to 2, n equal to 3, and so on. Then uxt times t is equal to C4 cos n pi x over L times C1 k lambda t. This is going to be C4 times C. I'm going to say, okay, it's going to be some Cn, because I'm going to put just Cn because I know that this constant is going to change for n equal to 1, n equal to 2, to n equal to 3, and so on. So I'm going to put just Cn. E k lambda t cos of n pi x over L for n equal to 1, 2, 3, and so on. So then that means I have the solution C0 when I say lambda equal to 0, and I have Cn e k lambda t cos n pi x over L. Where I know this lambda I'm going to sub later. I got this. This is for when n equal to 1, 2, 3, and so on, right? This is for when n equal to 0. Just like that. Yeah, so okay, then you just have to write u, the general function, that's gonna be just the summation for c naught, then c when n equal to 1, I start when c n equal to 0, then n equal to 1, n equal to 3, and so on, right? So just the summation n from 1 until infinity, cn k lambda is minus alpha squared. From where I got this solution came from setting lambda equal to minus alpha squared t cos n pi x over L. So that's your solution. Now you need to find C naught and Cn, right? I'm gonna use the initial condition. Initial condition is ux 0 equal to fx. That means I'm gonna set from here C0 summation n equal to 1 until infinity Cn e minus k alpha squared times 0 cos n pi x over L. Then just I end up with C0 plus summation n equal to 1 until infinity. You get Cn. All of these just gives you 1. Then you have cos of n pi x over L. This is just cosine Fourier series. So you just need to find Cn. As you remember, ux0 was given as fx. That means fx is also equal to the one I got, Cn cos of n pi x over L, like that. Then I can just bring it to the form of cosine Fourier series, which is you have a number here over 2, that's the form, plus 1 until infinity Cn cos n pi x over L. Then from here, whatever the coefficient is here is just 2 C naught, that is there, according to the formulas, 2 over L, 0 until infinity, until L, fx dx. From here, I can isolate C naught equal 1 over L, 0 until L, fx dx. Just write Cn equal to, and also from the formula, fx cos n pi x over L times dx. So that's pretty much your constants, because we are just given fx as a function. So then we just write the general solution, uxt equal to C naught. Then you just have that, okay, from here, you can just write from here equal to C naught. C naught is just the one that we got here, 1 over L plus summation from n 1 until infinity Cn, which is 2 over L integral 0 until L fx cos n pi x over L dx. That's your Cn. Then you have E minus K n squared pi squared over L squared time, and then cos n pi x over L. So that's your solution. That's all.